Hello everyone, and thank you for joining us for our webinar today, choosing the right drone for the right job. I'm Sean Rowlands, the European Sales Manager for Microdrones, and I'll be keeping everything on track today. We're grateful that you've taken some time to learn more about our solutions and especially some of the customers using our solutions. And we're here to support you, directly after this webinar and hopefully moving on into the future. So the main topics we'll cover today is a case study from Crafton Tull, sort of real world applications of microdrones, background of microdrones and our professional grade solutions, what is direct georeferencing and why it's a game changer. So I'll now hand over to Matt and he'll really dig into the detail properly. So without further ado, welcome Matt.
Hey, thanks Sean for the introduction. Hey guys, I appreciate everybody taking time out of their busy schedule to spend with us today. So today we're going to hop right into the agenda. Sean kind of hit on it first. We're going to get right into the meat and potatoes of this. So as soon as I get done, go over the agenda, we're going to pass it over to Nick and Jeff from Crafton Tull to get into their case study. Once they're finished, we'll go through a quick background on microdrones, hit on some key points of the solutions they use, such as direct georeferencing and what that is, components of UAV-based Lidar, and then we'll invite all the attendees to a special offer and finish up with some questions at the end and have some closing remarks from Sean. But without further ado, we're going to pass it over to Nick and Jeff from Crafton Tull, who's going to hop right into a project they completed.
All right, thanks for the introduction, Matt and Sean, the whole Microdrones team. We really appreciate the opportunity to present to you guys about how Crafton Tull is using the Microdrones product in our current workflows, specifically as it relates to a project that we recently completed in Tennessee for a client of ours. As Sean stated, I work for Crafton Tull and Associates. We're a multidiscipline firm in Arkansas and Oklahoma. We currently have 8 offices across Arkansas and Oklahoma and are looking to add a couple of more in both those states. We have dozens of professionals across all of our offices. Jeff and I currently work in our Conway office and lead the UAS division out of Conway. As you can see, we've got numerous field crews and professionals all across Crafton Tull, and the biggest thing that I can say about the company is that we kind of pride ourselves of being on the leading edge of the technology, investing in new technology and implementing that into our current workflows so that we can give our clients the best product possible. So as you can see, over the course of the past 30 or 40 years, kind of where surveying has come. So for all of you that are in the surveying and mapping industry, we've gone from theodolites, total stations, to now surveying with drones and being able to give our product or give our clients the best product possible, sometimes by not even setting foot on the site. So without further ado, we'll kind of jump into this project that I want to be speaking about today. We had a client come and they wanted a 7-mile highway corridor of new highway construction to be surveyed. So our task was a topographic survey. The client wanted a classified point cloud and up-to-date ortho imagery so that they could produce a high-resolution surface model that could be used for quantity verification from construction to as-built. And so we were given from the client essentially a CAD file that contained the center line of the route, the right-of-way, and any existing control points that they might have had on site. And this is what we use to kind of start the planning process and get going. And so as soon as they sent this to me, after review on the site, I could see that the microdrone solution was going to be the right tool for the job based on the terrain, based on the size of the project, as well as some of the obstacles that we'll get into later in the presentation. So our initial planning for this project presented several challenges. Number one, after looking at the project in Google Earth and on some quad maps, we noticed that there's a lot of terrain change on this site. sometimes as much as 150 to 200 feet from edge of right-of-way to center line. The size of the project, 7 miles, sometimes right-of-way getting as wide as 500 to 600 feet. The client wanted a pretty quick turnaround, so 2 weeks for the full survey from start to finished product. Some of the other challenges are line of sight and adhering to the FAA Part 107 rules. And then we have the challenges of stuff that we can't control, like environmentals and weather. As we all know, weather wreaks havoc on surveyors. So our initial planning was done in the office, mainly through CAD and Google Earth. Our initial plans were to have 22 flights, 13 with the Lidar payload and 9 with the ortho imagery payload. We were going to utilize multiple takeoff and landing locations. With this being a new construction project, the research for takeoff and landings on Google Earth was fairly limited. So we kind of did some preliminary hotshot locations that would soon be adapted in the field once we actually got on site. So once we developed our initial plan using Google Earth and AutoCAD, we use the MD cockpit software from Microdrones on our Android tablets to start building some flight blocks. And we generally go ahead and pre-build all of our flight blocks in the office before we get to the field to save a little bit of time and be more efficient once we get there. So we would export KMLs directly from Google Earth or AutoCAD and then use those to build the flight blocks. What you're looking at here is a screenshot from the MD cockpit software specifically for the Lidar payload. We flew this entire corridor at 50 meters, right at 160 feet with the Lidar payload. We flew at 4.5 meters a second, which is nearing the top of recommended speed from the manufacturer, Microdrones, for the Lidar. We ran at 60% lateral overlap, so each one of our flight lines would overlap the next one by 60%, good coverage on the site. We utilized the same takeoff and landing locations each flight, and then we would generally fly 1 or 2 flights from those takeoff and landings, so that way our field crew could monitor the flight from takeoff to landing and would not have to move actually during the flight. We use alignment waypoints at the beginning and end of each flight block to make sure that our trajectory and our orientation is proper during the post-processing. And then we use a neat feature that Microdrones has built into their drone payloads and their units called terrain follow. We use this on all flights. This ensures that the UAV stays at a consistent height above the terrain throughout the duration of the flight. This is a key factor in making sure that your data is consistent whenever you're outputting your point cloud or imagery and creating your deliverables. So what this yielded for Lidar was plus or minus 30 acres per flight and about 0.6 miles center line length or right away for each Lidar flight. For the ortho, same workflow, just a little bit bigger flight blocks, because the ortho imagery is a lighter payload. It has higher flight times. So we flew our ortho imagery at 120 meters, close to 400 feet high. We used a little bit higher lateral overlap and at 70% and a 70% forward overlap. So back front, side to side, we had 70% overlap on all of our images, which is key in tie point extraction for our imagery. Again, we use the same takeoff and landing locations for each one of these flight blocks, but these actually differed from the Lidar flights due to the length of the ortho blocks. We would, scout these takeoff and landings probably 2 or 3 flights in advance, so we kind of knew where we were going. Same workflow with the alignment waypoints, one before, one after. Again, ensuring that we have proper GPS orientation with our trajectory. Using the terrain follow feature for imagery ensures that we have a consistent pixel rating or ground sample distance for our imagery all across the project. And since these flight blocks were a little bit bigger, we got a little bit higher in acreage, 55 acres or about 0.8 miles of right-of-way. So these are just average numbers for this corridor project. I know that the Microdrones quad can do quite a bit more acreage, you know, if you're just doing a square or a tract of land. So what our fieldwork timeline looked like from start to finish for this, which I think is kind of a key aspect. So we left Monday morning from Central Arkansas, got to the site about 1:30, and this UAV is so easy to use, put together, and get going that by the end of the day, we had already flown 3 flights using the Lidar payload. So the next day, since we had already scouted the site, we were able to accomplish the remainder of our Lidar flights, 10 Lidar flights, starting at 8 a.m., finishing at 5:30, still had plenty of time for a decent lunch. On Wednesday, we came across and set all of our ground control points for our imagery flights, and then we set some ground control points for our Lidar check shots. Since Lidar, you know, doesn't require the ground control points during processing, they're merely surface check shots. We didn't have to set those prior to our Lidar flights. The ortho imagery requires the ground control points. Obviously, you're taking pictures of them, so those had to be set before the flights. Then we had a slight rain delay on Wednesday afternoon. On Thursday, we showed back up, good weather. We conducted 9 ortho flights from 8 to 5, so we flew the entire 7-mile corridor for imagery in one day. You can kind of do the timing on that. That's about an average of 1 flight per hour. That includes setup, tear down, takeoff, landing, actual flight time, and then moving from location to location up and down the corridor. On Friday, we spent the morning in the hotel room, as we usually do, doing data verification to ensure that we had all of the data that we needed before we left the site. So we just kind of ran some initial checks on the Lidar and the imagery itself, just some initial quality control checks to ensure before our field crew left the site that we had all the information that we needed. So our total time on site was 50 hours, including travel time and delays. That's 5 days for 1 2-man crew to survey 7 miles of corridor. The processing time on this, these are kind of conservative numbers, but for the most part, it took us 2 days to process both the Lidar and ortho imagery. The Lidar is by far faster and easier to process than the imagery. I think with our imagery, we had probably close to 2,200 images total from all 9 flights. Each one of the images at about 40 megabytes apiece, very high resolution. So it takes a little bit to turn that image out and to create the ortho mosaic. Then myself spent 2 days in the office sifting through the Lidar and preparing the actual deliverables that we sent to the client. So just ensuring that we had good quality ground data, classifying the point clouds, extracting bare earth models, stitching our flight imagery together to create a one cohesive ortho mosaic, and then doing some image compression and tiling for the client. So all said and told, 8 to 9 days to complete this entire project from start to finish. That's not bad. Our software suite, these are just a few of the ones that we use, but kind of the main key components. Obviously, we use the MD cockpit for our flight planning and execution. We use the POSPAC UAV to post-process all of our flight trajectories with our TO2, our TO4 files, all of our GPS files. We use the MD Lidar, the proprietary processing software from Microdrones, to create and georeference all of our LAS point cloud files. Then we use a Trimble software suite to classify those files, build all of our elevation models. We use UAS Master to produce our imagery. You can also use software such as Pix4D to kind of yield some of the same results. And then we ended up finally in AutoCAD Civil 3D. This is where we're going to bring in our surface models from TBC and our imagery, put all of our deliverables together, and create and edit our contours. So this is kind of what the point cloud looks like, a screenshot. What you're looking at is just a portion of the corridor. This is after initial classification. So we run a standard 5-category classification on our Lidar to kind of simplify the process. 1 is ground, you see in brown. 2 is vegetation, you can see in green. 3, poles, lines, and signs, which are all going to be in red. Power lines in yellow, and all of your buildings will be classified in a blue color. And then all of the remaining, which you can see up and down the middle of the corridor, that's going to consist of cars, some taller grass or lower vegetation, and basically anything that doesn't fall into the parameters for the other classifications. So this is important to ensure that we get down to a ground classification or a bare earth model before we start building our elevation models, our surface models, and our contours. So this is a digital elevation model that was created from the ground extraction. This used every point in the ground extraction. No sampling was done, so it was a very high resolution elevation model. This elevation model is what we use to do our surface checks with our ground control points to ensure that all of our flights were processed correctly, all of our controls are within tolerance, and we're meeting the accuracies requested by the client. And then also, this is the same model that we would use to build our set of contours from, which you can see in this slide. So this is a full set of 1-foot, 5-foot contours that were created from the elevation model in the previous step. And these contours can then be dumped into your design software of choice, whether it be AutoCAD, Autodesk software, MicroStation, to build your actual tin file or your set of contours that you're going to design from. This is kind of a key component that we generally provide to all of our clients, whether they ask for it or not, just to give them a little peace of mind. So this is an accuracy assessment of the ground control points that we set along site. So we set 20 ground control points for the entire 7-mile corridor for ortho imagery and Lidar. This is a low number to those that are familiar with UAVs, especially those that run some of the DJI models or things like that don't have an RTK GPS in them. The Microdrones unit has a direct georeferencing, a Planix IMU to give high accuracy GPS, so the initial orientation of the photos for the imagery is really close. You know, we're merely using these ground control points to do very, very slight modifications in the imagery. And then over a bigger project, you're kind of ensuring that you make sure that you're factoring in a lot of your convergence angle scale factor across a long project. So our furthest check shot out was 35 hundredths. That actual check shot was one that we had set off the side of the road in the grass. And upon later inspection, we could see that in the triangulation model that we had not gotten a good ground extraction at that particular point, that we had kind of triangulated from the top of grass. And so we were able to clean that up a little bit before we created the final contours. Your closest check shot was flat. Our average on our hard surfaces were 13 hundredths. So this is along all the corridor of the asphalt and gravel. All of our soft surface averages, which were all the points we set out in the grass or on the right of way itself, were about 25 hundredths or 3 or 4 inches. So these are good numbers when it comes to actual UAV LiDAR data, and kind of what we found is these are kind of on par with what we see site to site, location to location, and dealing with GPS for the past 10 years. I can tell you that these numbers, when you're surveying out on the edges of right of way and in the grass, are pretty close to the same residuals that you're going to get from any GPS. So this is kind of where it really counts, showing the cost comparison of what it would take to do this same project, conventional methods or with a UAV. So on the left, you can see with two-man crews for this particular site, the terrain challenges, the length of the site, and the request from the client would probably require two-man crews and about 12 working days to get this done. So using some standard hourly rates and daily expenses, you kind of come up with a field cost of about $48,000 with the UAV and the time frame that we were actually able to get this done. We were able to do the field work in 5 days. Same average daily labor cost, a little bit higher day rate and expenses. And we're able to save the client 66% across the board on the field time. That's amazing. So these numbers and these savings are fairly consistent when it comes to field time across all of our projects. We generally see a cost savings on field of about 40 to 70%, depending on the size of the project, location of the project, and requests from the client for deliverables. So that's a good cost savings that can be passed on directly to the client or marked up on your bottom line, however you want to treat that. So what I'm going to do now is Jeff, our chief UAS pilot here in our Conway office, who's got more flight time than me, has been surveying, for 16, 17 years. And so what I want him to do is just kind of speak from his field experience to some of the benefits of utilizing UAVs in surveying and mapping. Jeff?
Thank you, Nick. That was definitely a fun project to be on, and I'm glad I was able to be a part of it. So I'd like to speak briefly about how, since we have introduced the MD1000 into our workflow, the way we approach our projects and the efficiency in which we collect our data in the field has drastically changed. So primarily, we use it for large topographic surveys, quantity surveys, alpha surveys, design and planning projects, and corridor mapping. So it definitely is a tool that we use on a lot of the survey services that we provide. If I could just get it to drive a stake in the ground, we'd be golden there. So, so the first and probably most obvious benefit is the ability to cover a large area in a single day. With the LiDAR payload, we can accurately and efficiently map and survey in a neighborhood of 200 to 250 acres per day. And with the DG payload, if we're flying for imagery, we can fly a little bit higher and a little bit faster. So with that, we're getting about 450 to 500 acres a day. Now these are Crafton Tull's numbers, so these will vary depending on the survey crew. Some people may be able to get more, some may get less, but that's kind of what we're getting. So as you can see, projects that used to take several weeks are now taking a day or just a few days to complete. So we're able to save valuable time in the field. The MD cockpit interface is very user-friendly. We have the ability to quickly and easily create and manage our flights in the mission editor and flight data. So once again, that saves us time in the field. On the back end, the MD LiDAR processing is very user-friendly as well. Once we get the data out of the LiDAR and run it through POSPAC real quick, we're able to put that through MD LiDAR, and then it quickly gives us our LAS files. And with those LAS files from there, we move into Trimble RealWorks and Trimble Business Center. And usually, we can be in the field one day, and then that evening we have our LAS files ready to go, and by the next day we have a surface and a set of contours. So as you can see, it's a complete game changer. The quality of the data that we're seeing is unparalleled. With the SICK LiDAR unit, we're getting multiple returns, so we're able to penetrate the canopy and then get some lower vegetation and then get ground data as well in some pretty heavy timber. We've worked with other UAVs in the past, but what we're seeing from the MD-1000 is superior to what we've gotten in the past. We've had positive feedback from our design team and our engineers here at Crafton Tull, as well as other engineering firms that we've done work for. Since we've been using the MD-1000, we've gained several new customers and clients who are giving us repeat business. So, the investment has definitely been worth it. Another key area that the UAV comes in handy is from a safety standpoint. A lot of times surveyors are in areas that may pose danger, such as high traffic areas, large construction projects with a lot of moving equipment, treacherous terrain, anything like that. So with this, we have the ability to safely collect that data remotely, and so that's really huge for us. And then kind of on that same topic, inaccessible areas that are really difficult to get into, it might take up a lot of time trying to get into and traverse. We can collect the data in there using the quadcopter as well. And then finally, the microdrone support has been key to us. They, if we've ever needed anything, they are right there with us. Matt and the rest of the folks at Microdrones, they're always, so when we're on a project, we kind of feel like we're right there. They are right there with us on the project, and we really appreciate that. And once again, we thank Microdrones for giving us the opportunity to speak about one of our projects. We really love what we do, and we love to talk about it. So thank you for this opportunity.
For sure, Jeff. I appreciate it, man. That was really powerful stuff from you and Nick. This is back to Matt. Hopefully everybody can see my screen now. I just gotta thank those guys. That's really powerful for them to go in and actually show every detail, and they paint a really great picture of how that project went down, and everything it takes in order to complete a successful mission in that sense. Back to the agenda real quick. Obviously we just had Crafton Tull go through everything. So from here, we're going to just hop right into just kind of talking about the pieces that they use on this project and the benefits and the technology behind those individual pieces. So without further ado, talk a little bit about Microdrones as a whole. So for those of you who aren't familiar with us, so Microdrones is the oldest commercial UAV manufacturer. We're founded in Siegen, Germany, with other global offices, including those in China, Dubai, Australia, Toulouse, France, Montreal, Canada, where our payloads are all integrated, and here in the U.S. On the old Griffiths Air Force Base in Rome, New York. That's actually one of the FAA test sites around the country, so we do a lot of our accuracy assessments and beyond visual line of sight testing, all that kind of good stuff there. So Microdrones, we actually focus on providing a full solution to our customers, not just a drone, not just a payload, but a cohesive unit focused on surveying and mapping. This sets us apart in this field and allows for us to do things such as build things into the mission that other manufacturers cannot because of the integration of our systems. Our systems are purpose-built for surveying and mapping, and in order to get the most out of them, we put a very large emphasis on training. We see training as a key element to ensure safe and efficient missions. It's crucial. It's a very crucial component to be able to operate the system safely and maximize your return on investment. We'll touch a little bit of this on. We'll touch a little bit on that later. So back to our solutions, everything's under our MD Solutions umbrella, with MD Mapper and MD Lidar being our main focus today. A full solution in our mind isn't just a drone and payload, but the necessary software, training, and support to complement the system as well. Crafton Tull uses all these pieces brilliantly, and we'll spend the next 10 minutes or so just talking about what those pieces are. So the first piece being, the vehicle in this. So in this case, Crafton Tull, they flew the MD-1000, which is our flagship airframe. I would say, it's actually 10 years old this year. So another big focus of ours is building a system meant to grow with your organization. So as new technologies comes out, we're not building a whole new airframe. around payloads, but integrating new payloads into the existing airframe. So it's truly a system meant to grow with you. On all of our systems, from the 200 that you see over here, which was the first ever commercially built quadcopter, up to the 3000, our motors are all rated for 10,000 hours. So they're designed to keep you flying with little to no downtime and maintenance. The 1000 that we've been focusing on today kind of does it all, from photogrammetry to Lidar to inspection with both visual and methane gas sensors. And then the 200s you see over here is strictly just a nadir mapper. And finally, the 3000 that you see here in the middle is our heavy lifter, meant to carry your more robust Lidar payloads and medium format cameras. So enough about the actual vehicles. Let's get into some of the things you might have heard, throughout the lead up to this presentation and throughout Nick and Jeff's presentation as well. So some of the buzzwords that you may have heard are, are direct georeferencing, or DG. What is DG? So when using photogrammetry payload, DG is a process of determining the exterior orientation of each trigger event without the need of aerial triangulation. So what that means is you not only know the precise northing, easting, and elevation of the position of the drone and the camera in 3D space, but also the omega phi kappa angles, or the roll, pitch, and yaw of that sensor at each trigger event. So this is achieved by using a very highly accurate GNSS receiver and inertial sensor, and in this case, it's the APX-15 from Trimble and Aplanix. What some of the benefits of direct georeferencing is the ability to reduce or eliminate ground control points. So as surveyors, you guys will know that you never actually are going to get rid of ground control, but with the use of aerial triangulation, or with the use of direct georeferencing, you're not actually using those ground control to determine your exterior orientation of your image, but using them as strictly as checkpoints. Some other improved collection of some other features of direct georeferencing is it allows you to be more efficient in the field, so you can reduce the amount of front lap and side lap down to 60-40 with this solution. If you're flying an area map, that's plenty. For corridors, usually you're gonna, you can fly down to 1 or 2 strips with this system. It's because of knowing how each pixel is orientated on the ground from that INS system. It also, if you do use aerial triangulation, still it improves the point matching efficiency, so you're able to localize your ground control much simpler. And then obviously the corridor mapping and ability to map hard to access areas. So since you're not actually using ground control in those areas, you can use them outside of the hard to map areas as a checkpoint, and use the INS system on board the drone to actually georeference your photos out in that space. The workflow, which Nick and Jeff touched on, is pretty simple. So when you get in the field, you're actually going to have a local base station logging static data. So be it a Trimble base station, you can get a T02 file, or any other type of base station, that can record a Rhinex file. You just want to make sure your base station is recording at 1 second intervals. The drone's actually going to be recording the static data as well from the GPS, and all the inertial data from the IMU. Once you land the drone, after you build your mission and fly it with using ND cockpit and in the field, you'll take the T02 file, the trigger event, or the trigger event file, the base station file, and your images, and you'll marry those together in PodSpec UAV. That will give you a text file of your trigger events of your images. You'll then take your exterior orientation file with your images and build your deliverable, or build your orthos in the photogrammetry software of your choice. And output, your digital surface model, or your orthomosaic. In this case, is what Crafton Tull used this system for. Some benefits that you can kind of visualize here, with this is what most of you are going to be familiar with, the GNSS assisted aerial triangulation. In most cases, you're going to be flying 80-80, 80-60 front lap and side lap. And you're going to use ground control around the site in order to georeference your photos. With direct georeferencing, since you do know all the parameters of each image, you can reduce side lap and overlap, as well as use those ground control for checkpoints. And if you do global shift to get rid of any datum errors to one of those ground control, you'll see tighter data sets as well in the future. So the components of this system, obviously, is the NB4-1000 as the drone. The payload consists of a Sony RX1R2 camera, which is about a 42.4 megapixel camera from Sony. as well as the APX15 DG GNSS and IMU solution. With all photogrammetry solutions, you're limited to your GSD. In this case, your accuracy is 1 to 3 times your GSD in the horizontal, and 3 to 5 times your GSD in the vertical. The great thing about this camera, at a 400 feet or 120 meters, you still have a 1.6 centimeter per pixel resolution. So it's still, you can still fly high and still get those high accuracies in your deliverable. So moving on to Lidar, so many of you, Lidar is not a new technology, but it's becoming more accessible from drones. And what Lidar stands for is light detection and ranging. And there's 3 major components in an aerial Lidar solution, not including the vehicle. Those components are the INS or the IMU, the GNSS receiver, and the laser itself. So each one of these components has an error budget, and in order to get the most out of the payload, you have to minimize that error budget altogether. So this is actually done by what's called a bore sight calibration. The bore sight calibration uses algorithms, angles, and distances to calculate where that laser is in 3D space. Without a proper bore sight calibration, you can see misalignments in your strips and large inaccuracies in your data. So some benefits of Lidar, there's being able to process the data and actually know where your points are on the ground, from the process of direct georeferencing and using those IMU and the GNSS and the laser all together. You become more efficient in the office processing the data. Some benefits of Lidar are the ability to have multiple turns that Nick and Jeff hit on. So with the Indy Lidar 1000, you have up to 3 returns. And what that means, Lidar sends out thousands of lasers, pulses per second. And there's ability to have that laser, bounce off something and actually return back to the scanner multiple times. So it gives you more opportunities to penetrate through vegetation and actually get shots on the ground. So photogrammetry assumes the tops of the trees are the ground, whereas Lidar gives you ample opportunities to actually make, have that beam of light actually make it to the ground and give you points on the surface. Some other key components of Lidar is the ability to process the data quickly. With photogrammetry, you're not only going to see the tops of the trees or the tops of vegetation as the ground, but you're going to spend hours and hours processing that data. So if you don't actually need colorized data or an orthomosaic, you just need 3-dimensional data. Lidar is going to be much more efficient in the office after the fact as well. The workflow for the MD Lidar 1000 is very similar, or for any Lidar payload is very similar to a direct georeferencing photogrammetry solution. Instead of getting an exterior orientation file, you're using it's called an SBET, or your whole trajectory. So the drone's recording a T04 file, your base station's recording a RINEX or a T02 file. You then marry those two together in POSPAC UAV to get your SBET, or your trajectory. And that is, all the time, the entire flight, knowing how the northern easting elevation at a specific time interval, as well as your omega phi kappa angles. So when you get that post-process trajectory from your base station and your INS system, you then marry that with your raw scan data from the drone into our MD Lidar processing software, and that will actually build your LAS point cloud that you can output and view in other software suites such as Trimble Business Center or AutoCAD and whatnot. Some attributes, that you should look for when actually searching for a UAV-based Lidar solution. Is your workflow fully integrated? So or do you have multiple hands in the fire? Do you have somebody that integrates the drone or builds the drone? Somebody integrates the payload. Somebody builds the flight planning software. Somebody builds the post-processing software, and you have a bunch of hands in the fire. And when you do have issues, you have a bunch of finger pointing going on. So having a fully integrated workflow and one manufacturer to speak to on all these pieces is a huge component of what Microdrones does, and it helps you be up and flying and processing data more often. Another big thing is, pairing that laser sensor with a high precision INS or an IMU system. Microdrones, we try to use the best of the best when it comes to our INS systems. We utilize the Planex's APX-15 for our Lidar 1000 and the APX-20 for our Lidar 3000. And what this means is, we want to know precisely the position of our sensor in 3D space at all times. So it doesn't matter if you have $1 million scanner, if you don't know where it is in 3D space, your laser data isn't going to be good on the ground. So that's a very key component in searching for a UAV-based LiDAR solution. Another huge proponent of searching for a solution is a sensor with multiple returns. So in most cases, you want to be able to penetrate through vegetation with LiDAR. So if you just have one return, you're not going to give yourself a lot of opportunities to actually penetrate through the canopy. So a minimum of 3 is a good place to start looking at when you are using a solution of this case. Finally, a system with low maintenance and ability to grow with your organization. You don't want to spend hours and days and weeks, making sure that your drone is ready to fly. You're carrying expensive payloads. You want to make sure that you have a reliable airframe that's going to keep you up and flying often. And then finally, a strong training and support network we kind of hit on earlier, and what Jeff and Nick hit on. Being able to, have the manufacturer, or have, the dealers of the manufacturer be able to train you and get you knowledgeable and comfortable with the system is a very, very powerful thing. And being able to get somebody on the phone and talk to you, if you are having to troubleshoot something in the field is another key component to look in when you're actually searching for a solution of this case. The components of the MD Lidar 1000 that Crafton Tull used today, consisted of obviously the MD4 1000 drone. Our payload, this was our first LiDAR payload we released last January. It utilizes a scanner made by SICK, the Trimble APX-15 INS system, and it also has an RGB camera for colorizing the point cloud. So if you didn't need to fly for high resolution ortho, you just wanted a colorized point cloud, that's what this camera is designed for. It's a 5 megapixel camera that's triggering throughout the duration of the flight, and it's going to give you the ability to build an ortho just that's high enough resolution to colorize your point cloud if you needed it to. The workflow, obviously, we just went through, but the software included with this solution is obviously MD Cockpit for building your missions and flying your missions, which is an Android-based app. POSPAC UAV is the software meant to build your trajectory or your trigger events, which is the Trimble Planex program. That'll give you your trajectory file that you'll then use to marry with the scan data from the laser in our very own MD Lidar processing software. Here's a quick snapshot of the point density you can expect at the different heights and speeds. So Nick and Jeff, they said they flew at 50 meters and 4.5 meters a second. So they were in about the 45 points per square meter range, which in many cases is more than enough. You can get up to 45 acres or so of flights coverage in a single flight with this solution, depending on the height and speed that you're flying at. If you do need a denser point cloud or the vegetation is denser, you can slow it down to get a higher density. So it's very user friendly in the app, and it also this table is built into the app. So if you are actually trying to build a new mission in the field, you can see what your expected point density is based on the height and speed that you are building your mission at. So all of our solutions, since it's all integrated by Microdrones, are sent with a calibration report. We know the precise lever arm distances as well as the angles and your bore side calibration angles. We can actually have you update this in the field if you are on your own, if you were to start seeing misalignments in your strips, to keep you from having to send your payload back as often as you would with maybe some other manufacturers. And then finally, here's a quick snapshot of our MD Lidar software. This is a software that's meant to marry the trajectory file from POSPAC with the raw scan data. It's 4 tabs to go through. You have your configuration tabs that has your is where you input your lever arm distances and your bore side calibration angles. Your output would be your coordinate system, be it your state plane, U.S. state plane, NAT-A3, you have UTM, or a bunch of European and Asia coordinate systems as well. And then finally, your processing log is where you click process and you watch it build your point cloud. You're in this software for maybe 5 minutes after you build your trajectory file. So actually going through the whole workflow from producing your point cloud can take about 10, 12 minutes at the most for each flight. It's very simple, very easy workflow, and very powerful. So with that being said, we'll pass it over to Sean and see if Sean's got some questions that me, Nick, and Jeff can answer for our people in the audience. So thank you again, guys and girls.
That's brilliant. Thanks a lot. Thanks a lot, Matt. Thanks a lot for all the information we took there. I think it's quite important we sort of take the last point from Matt there in terms of the training. You know, you've seen some quite unique specialist solutions today, which can really improve your workflows. So the ability to bolt on that specific training and bring yourselves up to speed, you know, get yourself to expert level very quickly, is quite an opportunity. Again, on the question side of things, thanks for all the questions we had so far about the products and applications. If you have more questions about the offer, please do drop them into the GoToWebinar tab on the right hand side, and we can pick up on those as well. If there's something outside of the webinar or anything else that you can think of later on, do come back to us via our website, where you can drop us an email or go into any of the products with a bit more detail. Okay, right, so let's have a look at some questions here. Okay, so why did you choose a system for this job? How do you determine which system to choose for a specific job? So Lidar imagery. So I think meaning imagery or Lidar as a sensor. How do we choose what we use?
Yeah, I think, I'll answer briefly and then pass it to Nick because they're the ones who actually completed the project. But, it's all about, choosing the right drone for the right job, which obviously is the title for this webinar series, being able to choose a solution that's going to be able to complete the tasks in the most efficient manner, from the accuracy assessment or accuracy requirements of the customer all the way up to, the deliverables they're wanting. It's a very important piece to be able to have a system that can do multiple things. And that's, in my opinion, why, Nick and Jeff chose the solution they did for that project. If you want to add some more, Nick and Jeff, go ahead.
Yeah, you're right, Matt. I mean, we kind of evaluate the client's needs prior to any project. And when the client came to us and asked us for, obviously they wanted a point cloud and some up-to-date imagery. And as I highlighted in the presentation, based on some of the terrain issues on this project, the physical location with it being an actual highway right-of-way, and kind of needing some narrow takeoff and landing locations, we chose the quad. And then obviously we wanted to implement the Lidar sensor because in our experience it's the best way to collect any ground data.
Awesome.
Okay. Brilliant, that's great. Right, so let's have a look at another here. So this was a linear mapping project. So I think the question's referring to corridor mapping. Back to Crafton Tull, really. Do you conduct many of these types of projects, and are the saving on the linear projects the same for area projects, so something less linear?
Yeah, so we do a lot of corridor mapping, and then we do a lot of large scale, small scale aerial mapping projects of just tracts of land. I think your cost savings kind of varies from project to project. The higher acreage in the project, the longer duration that you're actually in the field, probably presents a higher cost savings versus a very small project, at 5, 10 acres. But as I highlighted in the presentation, our general cost savings on field time generally is about 40 to 70%.
Okay, that's brilliant. No, thank you. Slightly longer one here. I will speak a bit slower. You mentioned in the field you are more productive and can collect the data required for this type of project in less time and with less people. Is there a similar saving for the office time?
Yeah, so the office time, yes, there is, but I'll say this: a lot of the office time in the processing is based on several factors. Number one is experience. So in the beginning, we were, kind of much slower trying to figure things out when it comes to software and the fastest, most efficient way to create deliverables. Two is the size of your processing computer. Your standard laptop you buy from Walmart or Best Buy is not going to be near as good as a custom-built workstation. So we have very expensive, very nice, well-built drone computers that do a great job in processing. And then finally, I would say for an office cost savings is going to be directly reflective of your processing team. How well do they understand photogrammetry? How well do they understand Lidar? How the data is collected, created, stitched together, and then packaged up into a deliverable. So in the beginning, we were far less efficient than we are now. Obviously, if you want to compare direct times, importing a CSV file of 10,000 points versus processing 150 million, there's a little bit more time involved. Yeah. So I think it's give or take, but it's directly reflective on the other factors.
Yeah, and that same goes for that in the field as well. The drone itself, the Lidar payload, and the camera, they're just the tools. You need the right people and supporting equipment, to make those tools work for you. So.
Well, we really appreciate your time, Nick and Jeff. That's great, great feedback, great answers, and I really appreciate everybody hopping on the webinar today. So thanks for those great questions by everybody in the audience. If you have any more, make sure to ping us or add them into the GoToMeeting window, and we'll be sure to have somebody get to those as quickly as possible. But Sean, I'll let you close it out. But thanks everybody for joining us today.
No, thank you very much, Matt. No, that's brilliant. So, a big thank you to Matt, Nick, and Jeff. I really appreciated your input today, and I think everyone will have taken a lot from what we've spoken about. Again, if you've submitted a question, we will be coming back to you very soon, and start that conversation with you, and hopefully be working with you a lot closer in future. So to you all, really a big thank you from Microdrones. And there's lots of exciting things to come and exciting projects to work on. So have a great day, and hopefully we'll hear from you soon. Thank you.
Thank you.